So let's finally talk about fundamental theorem of calculus number 2. So fundamental theorem of calculus number 2 is if f is continuous on an open interval I containing some number a, then for every x in the interval, this is going to be true. If we take the derivative with respect to x of the integral from a to x of a function, we're going to say f of t with respect to t. The big reason we have that is because we don't want these variables to be the same as that variable. Then this is equal to f of x. So if we have a continuous function on some interval, then the derivative of that integral, they're going to cancel each other out. So let's look at this problem. And this problem specifically says simplify the given thing, so the derivative of the integral from negative x to x squared of cosine of t dt without using FTC number 2. And we're going to do this without using FTC number 2 to prove a point. So the first thing we're going to do is we are going to predict what it would be like to use FTC number 2. Based off of what they gave us, which is not a lot, a thing that people might think it would be is cosine of x or cosine of x squared would make sense because we plugged in x. So those would be the two that most people come up with. So what we're going to do is we're going to look at this and we're going to do both things. So we're going to do the integral of cosine, plug in our intervals, and then we're going to take the derivative of it. So if we have the derivative of the integral from negative x to x squared of cosine t dt, the first thing that we're going to deal with is this integral. So I want the integral from negative x to x squared of cosine t dt. This right here, the first thing that we're going to do is the integral of cosine. So we can think back to our sine and cosine derivatives. So these going down are our derivatives, going up are our integrals. So I have cosine. So if I go up 1, we know that sine is going to be our function. So we have sine of x on the interval negative x, or sine of t, sorry, on the interval of negative x to x squared. Now with our original fundamental theorem of calculus, we would take this and plug in our top bound and subtract our bottom bound. So we'd have sine of x squared minus sine of negative x. So right now we have the integral of this inside piece is equal to sine of x squared minus sine of negative x. So we want to take the derivative of this. So sine of x squared minus sine of negative x. So we're going to do that down here just so we have a little bit more room. So we want the derivative sine x squared minus sine of negative x. Well, both of these are going to involve chain rule. So the derivative of the outside function, which is sine, is cosine. We keep the inside the same, and then we multiply by the derivative of the inside. Well, the derivative of x squared is 2x. And we are going to subtract the derivative of sine, so cosine of negative x, and the derivative of negative x is negative 1. And then I might rewrite it, so it is 2x cosine of x squared minus a negative, we're going to add cosine of negative x. So what we actually get is this, which is different than what we may have been expecting to get based off of how the function is treated to begin with. So here's the thing about FTC number 2. So the thing about this theorem is that I think it's a liar, and I think it's gaslighting you into thinking that it's not something more than what it is actually. So we're going to rewrite this in a slightly different way. So we have the derivative of our original piece here. And that piece is a to x of f of t dt. If we went through the steps, we would have to integrate this. So integrating it would be what we call capital F. We would plug in our interval, and then we would take the derivative. So all of these things are things that we have to take into account. So what I know is that we need to take the integral and plug in our interval. So our integral is going to mean that we have f of x and f of a in our problem. But because we're also taking the derivative, we're going to be sticking with this original function. So we have f of x minus f of a. The next thing that we have to keep in mind is that x in a could be something besides just a number or just 1x to the first. So we also have to incorporate chain rule into this. So we're also multiplying this by the derivative of that top bound and the derivative of that bottom bound. So when we're looking at this, the reason why everything goes away is because if a is a constant, this goes to 0, which means 0 times this is all going to go away, which means we're not subtracting any of this from our problem. On the other hand, this, the derivative of x, is 1, and 1 times f of x is just f of x. So all of this goes away, but when we're looking at these problems, we have to know that they were there to begin with. So I like to call this the liar theorem, or talk about how it's gaslighting us, because it is more to it than we actually think. And it becomes apparent with that when we have these bounds of things that are not just x to the first power, or we have more than 1x. So here is where we might use this. Simplify d over dx with the integral from negative x to x squared with the natural log of t dt. Well, we don't actually know what the integral of natural log is. And to find that integral, we actually have to do a lot more integration, and we have to use some special techniques. So we can use this formula to kind of help us out. So we're going to take our function natural log, and we're going to plug in x squared and negative x in for our intervals, in for t. So I have the natural log of x squared, and we need to subtract the natural log of negative x. We need to multiply this by the derivative of x squared and the derivative of negative x. The derivative of x squared is 2x, so I have 2x natural log of x squared minus the derivative of negative x is negative 1, making this positive 1 natural log of negative x. So this would be our answer. And there would definitely be some caveats here because natural logs can't have negative numbers in it, so we would only be looking at negative x values for this particular answer, but that is besides the point. So this is what we would end up we would use it for. The big things that we might see this in are problems where we have a function that is defined by an integral, so we are finding the areas, but then we need to find the slope or a derivative in there somewhere. So we might use that to kind of cancel each other out to get what we need.